Welcome to the 97th lecture of Digital Electronics. In this lecture we are going to deal some basic about counters and the procedure of designing a synchronous counter. Now coming into sequential circuits, that is the first introduction part. Sequential circuits. This is classified as synchronous sequential circuits and asynchronous sequential circuits. Now what is the specialty in these synchronous sequential circuits? In synchronous sequential circuits, what is the specialty is that clock is common. Clock is common, whereas in asynchronous sequential circuits, clock is not common. An example of this sequential circuit is counter. Okay. Now coming to the word counter. So what is basically a counter? Counter means it is used to count a sequence. It is used to count a given sequence. For example, it can be sequence can be 0, 1, 2, 3, again 0, 1, 2, 3, etc. Or it can have like another sequence, say 5, 1, 3, 7, again 5, like that. It can go like that. So counters can be used for two types of counting. So three types of counting. First one, given a sequence. First one is given a sequence. Given a sequence, the counter can count. For example, 5, 1, 3, 5, 1, 3, 7, 5, like that. It is a given sequence. It is known as a general counter. There is no specified word for it. Second one is up counter or down counter. So what is up counter? Up counter means the sequence will be in ascending order. Okay, and down counter will be sequence will be in descending order. Okay, and it should have all the values between that. That is, for example, if you are having 0, 1, 2, 3, 0, 1, 2, 3, it is basically up counter. And if it is a down counter, we can have 3, 2, 1, 0, again 3, 2, 1, 0. The sequence will go like that. And if it is up down counter, it should be one area of one important point that makes is that it should contain all the numbers in between the maximum value and minimum values. Whether it is up or down counter. Now, third type of counter that is you need to have is mode. What is simply mode? Mode is the maximum or is the number of states. It's the number of states or number of values that a counter can count. That is known as mode of the counter or modulus of the counter. That a counter can count. That is, for example, if I am choosing this counter 0, 1, 2, 3, 0, 1, 2, 3, what is the modulus? Modulus is 3. Okay, it is modulus 4. 0, 1, 2, 3. It can count 4 states. It is 4. 5, 1, 3, 7. Again, modulus is 4. Okay, so you can have mode counters. Okay, now in the case of asynchronous counters, okay, now these given a sequence up down counter and modulus counter, these can be designed in synchronous pattern. Can be counted in synchronous pattern or synchronous counter pattern. Whereas in asynchronous counter, we can have up counter or down counter or given a mode. Mode will be given there. Okay, it can be either up. It can be either up or down. Okay, whereas if a sequence is given, okay, if a sequence is given which is in a random order, that random order cannot be realized using this asynchronous sequence circuit, whereas it can be realized using synchronous sequential circuits. Okay, so that is an introduction to counter. So counter is generally, and it is a basic building block of a sequential circuit, or what you can say is that it is an example of a sequential circuit. Now coming into design of counter. Design of counter. Okay, steps needs to be followed. Okay, so here I am going to deal with synchronous counter. Synchronous counter. Okay, asynchronous counter I will do it after explaining all the synchronous counter and some problems. Now coming into synchronous counter. So what is the first step which needs to be followed? First step is you need to find number of flip-flops. Find number of flip-flops required. Okay, that is the first step. So how to find the number of flip-flops? That is, capital N should be less than or equal to 2 raised to n, where n is the number of states in counting sequence. Number of states in counting sequence. And small n is the number of flip-flops. Okay. Small n is the number of flip-flops. Coming to step 2. Step 2. Choice of flip-flops. Choice of flip-flops and excitation table. And excitation table. That is, you can have 4 types of flip-flops. What is it? SR flip-flop, JK flip-flop, T flip-flop and D flip-flop. So you can design a synchronous counter based on any of these 4 flip-flops. You can choose any one and draw its excitation table. That is the second step. Third step, and I'm not going into detail about excitation table because excitation table is already dealt in the previous lectures. Now coming into step 3. Step 3 is draw the state diagram. Draw the state diagram. That means state diagram is a diagram showing all the states in which the diagram showing all the states through which the counter is passing. All the states through which the counter is passing. Through which the counter is passing, or the counter can count. Counter can count. So that is a state diagram. Okay, in detail explanation of state diagram will be explained while doing a problem. Now coming into step 4. Fourth step is derive minimal expressions. Derive minimal expressions for input of flip-flops. For input of flip-flops. That is, for example, if I am having 3 flip-flops, if the necessity is of 3 flip-flops, and if I am having JK flip-flop, I will have J1 K1, J2 K2, J3 K3, and I need to derive the expressions for J1 K1, J2 K2, J3 K3. So I need to derive 6 expressions. So I am having 3 flip-flops, and that is in JK. I need to derive expressions for J1 K1, J2 K2, J3 K3. That again depends on the excitation table. That again depends on the excitation table of these flip-flops. Okay, and that is the 4th step. Now coming into the 5th step. Again, if I am having again 3 flip-flops and it is T, I need to find only T1, T2 and T3. So that is the 4th step. And last step is now step 5. You need to draw the logic diagram. Step 5 is you need to draw the logic diagram of counter. Logic diagram of counter. Okay. And the last step, step 6 is you need to draw the sequence. Step 6 is you need to draw the sequence along with the clock. Okay. So these are the 6 steps needs to be followed. So first step is find the number of flip-flops. Second step is decide which flip-flop you need to choose and draw its excitation table. Then third step is draw the state diagram. Fourth step is derive the minimal expressions for inputs of the flip-flops. Fifth step is draw the logic diagram of the entire circuit. Then last the step is draw the sequence along with the clock. Okay, so that is a general pattern. Now I will start with one simple example here. Okay, one simple example. So I will deal with design. Question is design a synchronous 3-bit up counter. 3-bit up counter. Okay. Now already it is given that it is 3-bit. Okay. So what is 3-bit? It can count from 000 to 111. Okay. And each flip-flop can store only 1 bit. Therefore, number of flip-flops required is 3. Number of flip-flops required is 3. So that is, if the question is given like this, you can have number of flip-flops is required is 3. Again, since it is 3-bit, you can count from 0 to 7. So it is also known as mod 8 counter. Mod 8 counter because it has 8 states. That is 0, 1, 2, 3, 4, 5, 6 and 7. So you will get 8 states. That becomes, it is also known as mod 8 counter. Okay. Now for the design. Okay. So since it is 3-bit, I am going for this number of flip-flops and taking it as 3. Then mod 8 counter. So second step, I need to so first 2 steps is over, right? Number of flip-flops is over. Now second step is I need to go for this one. Which flip-flop I need to choose? Okay. So here I am going to choose. This is step 1. Step 2. I am going to choose T flip-flop here. It's an easy one. Choose T flip-flop. Now, how to draw the excitation table of T flip-flop? Okay, I need to draw the excitation table of T flip-flop. So I can have present state, that is Qn. Next state, that is Qn plus 1. What is the value of T? Can have 0 to 0, 0 to 1, 1 to 0 and 1 to 1. If it is T, 0 to 0, it is 0, 0 to 1, 1, 1 to 0, it is 1, 1 to 1, it is 0. This T means it is basically toggle flip-flop, and if the state changes, this is an S state, then only value of T is varying. So step 3, I need to draw the state diagram. Now see, it is varying from 0 to 7. That means I should have 0, 0, 0 for state. Now comes 1. 1 is 0. This is 1. 1 is 0, 0, 1. Now comes 2. 2 is 0, 1, 0. This is 2. Now comes 3. That is 0, 1, 1. This is 3. Then comes 4. 4. That is 1, 0, 0. That is 4. Next one. That is 5. This 1, 0, 1. 5. Now comes that is 6. That is 1, 1, 0. 6. Now 1, 1, 1. That is 7, and it will come back to 0. So how it is counting is, it will count like 0, 1, 2, 3, 4, 5, 6, 7. Again back to 0, 1, 2, 3, like that it will count. Okay. This is the counting sequence, and this is the state diagram along with the states in which it is going. So it has states from 0 to 7. Now, if present state is 0, next state is 1. Then comes next state is 2. If present state is 2, it will become 3. Now, first of all, I will draw with all the present state and next state. Okay. So I am having present state. I am having 3 bits. That is Q3, Q2, Q1. Okay. And next state I am having Q3, Q2, Q1. And again, what is T? I am having T for 4, so I should have T3, T2 and T1, since I am having 3 flip-flops. So present state. First is 0, 1, 2, 3, this 0, 1, 1, 4, 5, 6 and 7. Okay. Now look to state diagram. If present state is 0, what will be next state? Next state is 1. So you have 0, 0, 1. If present state is 1, next state is 2. 1, 2. 2 you will have 3. 3 you will have 4. At 4 you will have 5. That is 1, 0, 1. 5 you will have 6. That is 1, 1, 0. At 6 you will have 7. At 7 you will come back to 0. Now I have drawn the present state, next state. Now look to T3. That means if you are looking to T3, you should look only through present state of Q3 and next state of Q3. So 0 to 0, it is 0. 0 to 0, no transition, it is 0. 0 to 0, 0. 0 to 1, it is 1. 1 to 1, it is 0. 1 to 1, it is 0. 1 to 1, it is 0. 1 to 0, it is 1. Hope you have got. Here it is 0 to 0, it is 0. 0 to 0, 0. 0 to 0, it is 0. 0 to 1, it is 1. 1 to 1, it is 0, no change. 1 to 1, no change, it is 0. 1 to 1, it is no change, it is 0. 1 to 0, it is 1. Now coming to T2. Now coming to T2. 0 to, that means here you need to consider only Q2. 0 to 0, no change, 0. 0 to 1, 1. 1 to 1, no change, that it is 0. 1 to 0, it is 1. 0 to 0, no change, that is it is 0. 0 to 0, 0 to 1, 0 to 1, it is 1. 1 to 1, it is 0. 1 to 0, that is change, so it is 1. Now coming into T1. 0 to 1, we have 1. 1 to 0, it is 1. 0 to 1, it is 1. 1 to 0, it is 1. 0 to 1, it is 1. 1 to 0, it is 1. 0 to 1, it is 1. And 1 to 0 again it is 1. Therefore what we can write? Therefore directly we can write the expression of T1. So we can write directly T1 is equal to 1. Directly from this one, because all the values are 1, therefore we can write T1 is equal to 1. Now you need to derive expression for T3 in terms of present state Q3, Q2 and Q1. Okay, you derive T3 as a function of present state Q3, Q2 and Q1. Okay, and T2 again as a function of present state Q3, Q2 and Q1. Okay, and T1 is 1. Otherwise you need to derive T1 as a function of present state Q3, Q2 and Q1. But here since all values of T1 is equal to 1, I can give T1 is equal to 1 itself. Now I am going to derive T3. What is T3? T3 is 1 here. So T3, I am not going for K-map. I can take it there because I am having only 2 ones here. So what is T3? Yeah, okay. So so what is T3? It is Q3 bar, Q2, Q1. So T3 is Q3 bar, Q2, Q1. Or here what you have? Q3, Q2, Q1. Or Q3, Q2, Q1. So here which is common? Q2, Q1 is common. Or and Q3 bar or Q3. A bar or A, that is 1. So what is the value of T3? T3 is Q2, Q1. So I have derived the expression for T3. Now similarly I need to derive the expressions for T2. Now if I need to derive the expression for T2, see, if you are looking to the columns of T2 and if you look to the columns of T2 and Q1 directly, so that is an easy way. Okay, if I am looking to the columns of T2 and Q1, both are exactly the same, right? T2 and Q1, 0, 1, 0 to 0, 1 to 1 it is same, 0, 0 it is same, 1, 1 it is same, 0, 0 it is same, 1, 1 it is same. So what is T2? T2 I can write it as Q1. T2 I can write it as Q1. So this is just by comparison. Okay. Now once present state and next state is over, you are allowed to only look to present state and value of T. So you got T3 as Q2, Q1, T2 as Q1 and T1 as 1. Now I need to draw the logic circuit, right? That is the next part. Okay. So this is first I will draw T3, the clock. You have Q3 and Q3 bar. Then next one, what is it? I have T2, Q2 and Q2 bar. Next what I have is T3, T2, T1, Q1 and Q1 bar. Clock is common. Since clock is common, I can give like this. Clock is common part. Now, what is T1? T1 is equal to 1. So I am giving 1 here. No problem. Now what is T3? T3 is Q2 and Q1. So T3 again write it as Q2 and Q1. So I am having an AND gate here. It is Q2 and Q1. So that I can give it to T3. Then what is T2? T2 is equal to Q1. T2 is equal to Q1. So Q1 is coming here. I'm taking it. So T2 is equal to Q1. So where I will take the outputs? Outputs are, I can take Q3 here. Q2 is another output I will take here. And Q1 is another output. Okay. Now my logic circuit is over. Okay. So here I am not showing the preset and clear. Okay. Anyway, preset and clear will be there in common. Okay. Preset and clear will be in common. No need to draw it, but it is it will be good to draw it. So it will have, you have preset and clear. Okay. So before any circuit to function, you should press preset and clear. That is it. This clear. Okay. So this is the basic logic circuit of mode 3 or mode 3 synchronous counter. Now what is the next step? It is not over. I need to draw the this one, right? The what? I need to draw the sequence, right? Now, so last step is draw the sequence diagram. Draw the sequence diagram, or what it is also known as timing diagram. It is also known as timing diagram. So how many clocks you require? You require almost there are 8 states. So 8 clocks are required. So I will write 1, 2, different pattern. So first you should draw the clock. This 1, 2, 3, 4, 5, 6, 7, 8, 9. It will go like that. So 0, 1. So this is basically the clock. Okay. So I will take the positive steering here. Next clock comes here. I am going for positive steering. For positive steering, and I'm going to positive steering. Yeah. So now I will draw Q3. What is Q3? Q3 I will show it as 4 zeros and then ones, right? Yeah. Q3 I will take it as 4 zeros, right? So it is 0, that is 1, 2, 3, 4, and then it will be changed to 1. So that is Q3 pattern. Now what is Q1? Q1 is like this. Sorry, what is Q2? Q2 is 0 0 1 1 0 0 1 1, right? Okay. So Then now coming into Q2, it is 0, 0, 1, 1, 0, 0, 1, 1. It will come back to 0, 0 like that. That is Q2. That is 0, 1. So what is Q1? Q1 is 0, 1, 0, 1, 0, 1. Like that it will go. So Q1, I am going to do Q1. It is 0. At this point to take to 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. It will go like that. Okay. So that is the sequence of Q1. Okay. So this is basically the sequence diagram or timing diagram. Okay. So here in this lecture what I have shown is a design of a synchronous counter. So the steps needs to be followed are find the number of flip-flops, choice of flip-flops, state diagram, and derive the minimal expression for J and K in terms of Q3, Q2, Q1, whatever it is. Then draw the logic diagram, draw the sequence. So I have performed an example for you using T flip-flop. Okay, and I have drawn the logic circuit, and this is the sequence diagram. Thank you.